Shivam, is there a way to start this from, I don't know, the meeting recording started 25 minutes ago. Is there a way to just end this recording and start a new recording?
Let me just stop and why it started half an hour earlier.
I don't know,
Oh,
I
okay,
think
okay.
somebody, yeah.
No, it is not started from half an hour earlier. I think it is started from um. Let me just stop it. Maybe. Oh wait,
Hmm.
we'll just cut the initial part out. Let
Okay,
it
take
be.
it. No worries. No worries, no worries. I think we are good to start. So, yes, hello everyone. Welcome to the NgKore Quantum Security Working Group. Um, nice to see you all. We were not able to, I think, conduct some of the previous meetings. It seems everyone was traveling at that time, but we are back. So happy to see you all. We have few things at the agenda. If you want to have a look at the agenda, I have pasted the link on the chat section. You just open it, try to, if you any other point, you can try it right there or just speak out loud. Right now is the correct time. We'll try to take all those points. Okay, I think I'm familiar with everyone who has joined. So I think we're good with the introduction part. We have few things in the agenda. I'll share my screen, first of all. This, mm, yeah. Can you guys see my screen?
Yes, sir.
Yes. So yeah, I think we missed to conduct some of the previous meetings. So this is the new month, July. There are 8 things in the agenda. Some of them are time taking, so we'll probably take it first of all, and then some are some basic discussion thing. And if there's any other business, you can just say it right now. So first thing is with the presentation that for which Satyam is here. He will talk about the tracing cryptography using eBPF. I know we discussed about this point couple of times in the previous meetings, but we actually never get the time to see the demo or have like a presentation. So that's why Satyam is here. So Satyam, maybe you can start with the slides or demo, whatever you have. I'll stop sharing my screen.
Hello, everyone. Am I audible enough?
Yes.
Yes, sir.
Let me share my screen. So I hope everyone has the basic idea of what we are trying to do. Although if not, let me just give a brief overview of what I'm trying to achieve here. So can you see this? Can you see my
Yes.
Yes.
screen?
Yes, Satyam.
Okay, so what I'm trying to achieve here is basically we do have some SAS tools and other tools where we try to trace the cryptographic bill of materials, and using those we plan some PQC migrations. But they are not feasible during the runtime. So most of the tools that you see, they cannot be run during the runtime because they have a very high overhead. But as you, if you are familiar with most recently when eBPF came, most of the sensors are now being written using eBPF because it has a very low amount of overhead, and basically you can just deploy it in your runtime environment and you don't have to do any code changes or anything to set it up, and it hardly takes one CPU and 1 GB of RAM to deploy the sensor. And I wanted to use eBPF to trace all the cipher suits and all the cryptographic elements that we need, to know about if we are planning to do post-quantum cryptography. For a company, it matters a lot that not a single point of error should be left, because usually it's that same point from where hackers exploit the system and get into your system. So I wanted to make sure to use it in a runtime manner, because during runtime we know that sometimes we communicate the algorithms down, meaning that if the client does not support PQC, maybe your server now is using a algorithm which is vulnerable. So if we want to know and have visibility into that, we need something that can trace during the runtime. So this is the basic architecture that I work with. So we have a user space inventory that sets up some eBPF programs and hooks. No need to dive deep into it. Just for example, what these are, they if you're familiar with what a kernel is, there are certain hooks in the kernel through which a packet gets processed. So eBPF leverages that and attaches to those hooks and tries to get all the packet information using those hooks. So some of those hooks and probes are present in the kernel itself. So those are called K probes, and some are present in the library. So those are called U probes. So I do use both K probes and U probes. And this is the basic architecture. Like the eBPF program sends all the packets to the user space using those probes. And in user space, we process those and stitch them together and create a C-bomb out of it. So currently I follow Cyclone DX 1.6 format for the C-bomb. Now, too much of talk. Now let me just show you the demo straight so you'll have a good, better understanding. Okay. Can you see my terminal? Can you see my terminal?
Yes.
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 Okay. Now I do have already a C-bomb generated, but I don't want to show this. It's too big. Let me just remove it and start from the starting. Okay. So now I'll just create this. So CipherTrace is running now. So I have attached to both the K probes and the U probes. So I attached to OpenSSL's U probe to get the OpenSSL certificates. So starting with the very basics of the things, uh, I just curl Google. So you can see that I curled on HTTPS. So it was using some certificates, and I have all that information over here, which is also written down in CBOM. So also it shows how many components are there. The components basically means the unique components and the number of sessions that I have. So let's say for one session, if you're trying to create multiple certificates, so it does not create a lot big list with the same source and destination IP. It keeps the metadata same and keeps the list of certificates, trying to make things less clustered. And in the certificate, I have all this DNS supports that Google has. And I also have the issuer and the dates, the validity for the certificate. And there are a lot of things that we can make use of here, like J3S and these algorithms, the cipher suit. The cipher suit comes from K probes, and the certificate information, which is this, these comes from the U probes. And I can also show you an example. Let me just open the CBOM also first. The CBOM is quite big, so it has a lot of information here. I can share it to you on the group for the curl command. You can go through it if you find something important in it. So what we'll be doing is we'll be making use of these cipher suits, and during runtime, if we see these, we can easily guess like if it is quantum safe or not. So I just added some verdicts here as well. But it's not only limited to a curl command. Now let me show you something where I run a AI tool call. Okay, let me just start it up as well. So I just send a simple message to Gemini, and we can also see all the cipher suits and certificates used in that. So you can see there is a TCP connection here. That's why, and it uses OpenSSL. That's why we have certificate information about that as well. So it traces AI certificates or any kind of traffic. But currently, there are some things not yet implemented in it since I currently use OpenSSL, so GoTLS does not work. I'm working on that part as well. So soon I'll be having support for GoTLS as well. Although Java might take a bit time because I'll need to build a different agent for it. Java works in a very peculiar way. So it shows two sessions over here. Let me just try to curl and increase the number of sessions. You can see it shows the binary that was calling the source IPN port and the destination IPN port, which is of Google's. And again, the certificate information and all. And there are four sessions here. So, and this is all added to the cbom.json. I can share this cbom.json file with you so you can go through it in detail. So this is mostly it. I didn't spin up some heavy load just yet because that might become too hectic to understand what is going on. So for now, I'll share this file. You can look through it. And if there are any questions,
Yes, Satyam. So you said you have attached a uprobe at OpenSSL. So what does that exactly mean?
so if you want me to go into the depths of it, that might take a lot of time.
Okay.
For to put it simply, it's just like what are shared objects.
Shared objects, yes.
So when you create an object file, generally binaries are linked using a shared object, and
Mhm.
there is a libSSL shared object that is always there in your PC, and lot of binaries use it. So in that
Mhm.
shared object, there are certain functions, and by attaching uprove, what I mean is eBPF injects its program into that particular function's address, and what happens is I can read that function's arguments and the return value it sends. So
Function
you
address is for your libSSL binary or is for something function inside your that
libSSL
binary?
shared object.
Okay.
It is this file. It's like this. Have you ever seen this file?
Yeah, yeah.
So it in this file you have certain functions and there are addresses in it. So the offset
Okay.
address. So we provide the offset where it has to attach. So it is a bit low level work. So that's why I don't want to go into the depths of it. That might take a lot of time. But to put it simply, it's just that it traces the function that is handling this packet. So the packet that was responsible for the function that was responsible to process this packet, it hooks onto that function, meaning that it injects a code before that function executes. And we are like reading all the arguments that function received. And when the function ends, we can read all the return values that function sends. So it, it basically sounds fishy, but it's not because, of course, we take permissions to deploy the sensor. And it does need privileges to be deployed in an environment. So basically, it traces all the arguments that is sent, and the arguments are, of course, the packet informations, the headers. So from those arguments, we capture that data and send it to the user space for processing. So that's how it works.
And what does Kbro do here?
Kprobe is used because for some currently statically linked binaries, the dynamically linked method does not work. But K-probes work in that case also because K-probes are the default path that every packet takes because it is present in your kernel rather than an application. So any
Hmm.
traffic that is coming in your system goes through a K-probe. And those are fairly, known K-probes in the world of sensors. Let me show you their names.
I mean,
Can't we
so
create a
what I'm trying
separate
to,
K-probes and try to trace it from there?
No, K-probes cannot trace the certificate information because it is encrypted in ASN.
I mean, is it possible to create a separate custom K-probes into the kernel?
No, 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 no. Then you'll have to create your own kernel, and then who's going to use your kernel? Why would companies use your kernel? It might be
But if
vulnerable, right?
but if they provide a capability to edit the kernel, right?
You no, you don't create new functions in the kernel.
Okay.
This is the network processing that's happening in the kernel. So let me show you. These are U probes, URET probes, and these are SSLU probes. These are the K probes. F exit and F entry are some new things. They use a concept called trampoline. But again, I don't want to go into the depths of it. It will take a lot of time. So why we don't edit the K probes? Because you cannot do it. It's not that easy. You'll be affecting a lot of kernel code. So that's one issue that people don't do that, and that's a very bad way of doing it because you'll be creating your own version of a kernel, and then who will be managing it, and why would companies use that? That's why they don't do it, and you cannot just simply add a function. There are a lot of checks for whenever you create a PR on the Linux kernel, there are a lot of checks. You cannot just add a function in it and call it a probe because that
Mhm.
can become a vulnerability later, and it will
And
slow down your kernel because at the end if you're adding a kprobe for ASN parsing, then that is very specific use case. So just for that specific use case, you don't want to create a kernel again.
and why ASN pass? Why ASN encrypted certificate is moved between client and server? I don't understand that part exactly. It's
uh,
encrypted form. That part I understand. But is it encrypted through ASN or is it encrypted through some algorithm?
ASN, there is a thing called DER in certificates. I forgot the full form. I think so. Aditya, are you aware of this concept?
Yes, actually, it's not
So
encrypted, it's just encoded. ASN encoded.
encoded, sorry, encoded is the right word, and that does not get supported in the K probes. ASN encoded, all data does not come in, and also there is a buffer limit in K probes.
Okay.
That's
So
why we
ASN
don't.
encoded data would basically go to your user space where the user space application will decode it, right?
Yes, yes, but here we don't have that luxury of having a user space because we are in the kernel, right?
Hmm. One more
So
thing
how you
then,
are
Satyam.
extracting? Yeah,
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 go
you
ahead,
go.
Shiva.
Yeah,
No,
so
no, go.
so how you are decoding the certificate from the connection?
I don't
Satyam?
decode.
Okay, so
I
you mentioned.
I intercept at a point where it has already been decoded.
Oh, okay.
Yes.
And can you name which exactly is that point?
It is a uprobe in the OpenSSL library, a particular function.
You prove, I mean, like a point. I understand you attached a program and at a you prove in the live itself, but which exactly point in the flow? Let's say before application or something what?
No, no, no. It is a function called D2IX.
Okay.
That is the function that receives the bytecode and passes it. So when it returns that bytecode, it has been decoded. So I intercept at that point and get the data.
But for the TLS 1.3, the certificates are actually encrypted with your symmetry key that is generated in both server and client side. So is it really possible? I'm not sure, like it is also encoded in that form.
I don't get it. What you're trying to
Uh,
say?
so the certificate in TLS 1.3, the certificate is changed between client and server in the encrypted form. Encrypted using your AES or maybe a symmetric key between your client and server.
Hmm.
Okay. So you mentioned like, the certificates are encoded, not encrypted. Encoding can be decoded, but encryption cannot be decrypted here.
No, that can also be decrypted because we are using uprobe. See, the whole point of using a uprobe is that you don't have to go through encryption, encoding, or anything because you're going into the libsys, that particular function where the encryption, decryption, everything has been completed and the bytecode is
Mm.
ready to be sent
Yes,
to the user space. So you don't
yes,
have
yes,
to
correct.
deal with any of those things.
Yeah.
Okay.
So basically,
मतलब मैं
whatever comes in encrypted format, it has to be decrypted, right? The certificate is also decrypted, but certificate is decrypted, but still there is a encoding layer. So then after also it is decoded, then it is where the U probe is coming. It's getting the
Yes,
certificate information.
and this only support right now. This only support OpenCell, right?
yes.
Okay.
But Satyam, how come? I mean, instead of these application thing, can't we just simply trace the traffic first of all? Like in the traffic, we try to get the client hello and server hello, right? I mean, this is not even, I'm not even speaking about the any application, any library, OpenSL, just simply the network traffic.
No, no, that will not work because first of all, there is a bytecode limit, and again, the encoding and decoding is a bit difficult to do using eBPF because at the end, eBPF will not be doing it, it will be sending it to the user space. And if we try to do something like that just using the network traffic and not any library, then that will, first of all, most part it would be impossible to do it because you'll be losing the keys, and secondly it will be lot time taking, and if it
Hmm.
is taking then it loses the whole point of running in a runtime environment.
But at least
Yes.
Satyam, like let's say the output that you have generated with this tool, to me it looks more similar to the what a Wireshark or TCP dump do
Yeah,
usually.
of course it will be similar, and it is a good thing because you cannot run TCP dump on a runtime customer's environment. You'll be slowing their whole system down. TCP dump is very costly, it has a lot of overhead.
Oh,
And
okay.
when you use this sensor, it is a very minor overhead. You'll barely even notice it until there is a very high amount of traffic. TCP dump, on the other hand, is a very big overhead.
Yeah. Plus, this can be used for observability, right? We can just run this eBPF and it will not be, I mean, it will not take much resources. It can be run for, let's say, some time. And if we
Something
do
like
this
forever, you can run it forever. It will just take one CPU
forever,
and
right? Yes,
GPU.
exactly. Yeah, but while doing TCP dump for a very long time, it's like what issue you get. It just
Yes,
slows
yes,
down
it is
everything.
very costly.
Yeah, and also Shubham, it's also slightly different from that because in that case we do the network traffic capturing, right? But in this case we are doing the OpenSSL symbols tracing, right? The whatever the OpenSSL libSSL is doing or libcrypto is doing, we're actually tracking that or tracing that point, not the actual traffic.
But again, except for the speed and the time it takes to capture it, the end goal, the end result will be the same around this level of information from TCP dump, or let's say another tool, let's call it Zeek or maybe. So,
Yes, yes.
so uh, from performance basis, how you think like this tool will be comparatively better than the networking tools like Zeek or TCP dump?
I
Uh,
think maybe I can answer this, Satyam. I mean, you can also add point on this. Zeek and TCP dump, they are doing network traffic, right? Their method is different. Also, I mean, the output can be similar, but they are also very resource constrained. And this eBPF can also be used in different deployment methods, like not just your host-based network traffic. Within the pod, whatever communication you do, we can also trace that with eBPF, with all cloud native environments. With some tools like Zeek and TCP dump, I mean, we can do it, but it's not very straightforward. And also, you can't run Zeek for the whole time if you don't have that much amount of resources. You want something lightweight. And I also believe one thing.
Resources is not the issue. The
Mm.
issue is that your application, it does not matter, you have infinite resources, but your application will face a bottleneck if you're running TCP dump. And actually, companies are paying, if you see the customers of Wiz Datadog, they're paying crores and crores of rupees for just these sensors because they are lightweight and they can run during the runtime environment. If you run TCP dump during runtime, no matter how many resources you have, but bandwidth is limited, right? You obviously hinder the performance and there will be a lot slow handling of the client traffic. That's why they pay this much money to sensors. There was recently a sensor that does something similar and it received around, I'm not sure, it received $1 million of funding just because it was really low overhead and it could run like for the whole time in the environment. So I've actually worked with customers who need this. I also had one client before who was ready to pay a lot amount for something like this. So because you cannot run it on a, what you'll be doing with TCP dump is you will take the application code to a corner or just run it for a very short interval. You cannot monitor it for the entire duration it is in the production. That is absolutely impossible with any other tool. And that is what matters at the end because you want to know during production is there any bug or something that is, using a vulnerable algorithm. That is the whole point. The point is not that you're seeing something that you haven't seen before, it's that you're seeing the things that you saw before but at the right time. Okay, you get the point. That is the point. It is not that this information you want, you will see it in Wireshark, but you won't see it when the application is running on production. That is the difference.
Yeah,
And where
and
this
these days,
particular
Shubham,
information
I
is
also
stored,
think,
Sorry, what
where,
what was
where
the
this
what
information is actually stored, Satya?
cbom.json? I mentioned about a file, right? That is the same.
Okay.
This is it.
Okay. No, actually, the information that was present before this, the network information. So that is not stored somewhere, right?
Which information?
the
Which is
information that you
book.
are seeing in the logs, Satyam.
Yeah.
They are stored. All that information is stored.
Where exactly, Satya?
See, in cbom.json, we have a format, right? So you can see
Yeah.
this location, file name, and we
No,
have
no,
the
that is fine. That is fine. I'm not talking about the CBOM related stuff. The when you run that particular binary, cipher trace, then there is some log generator, right? That looks like a Wireshark information.
yes, yes. I'm talking about that only. That is stored in this file, not in the same format, but in a cbom format. But the whole information is stored in this file.
But yeah,
See,
if you
the
want, we
type of
can also
sources.
store that in a log format also, Shubham. It won't be an issue, I think.
Yeah, but the whole point of using cbom was companies don't want it in this format.
Yes,
Hmm.
they can do this. I mean, they have like separate options. They can they
Yeah.
use existing tools like TCP-dump, and then they have something called CBOM generator, which passes this thing, and then it generates the CBOM. Here we have just removed that step. Everything we are just storing in the CBOM format. Yes, I think this could be modified slightly because let's say we don't want uh, like each of the session to have their own CBOM. So let's say if there is Satyam 10 handshake TLS connection, can that all 10 handshake come in just one cbom.json file?
They are in one cbom.json file.
No, like
They're not,
multiple
they don't,
sessions, multiple TLS
yes,
sessions.
yes.
Okay.
There is only one cbom.json file.
No, but this time there is one cbom.json file, but it's only mentioning the cbom for just one TLS handshake, right? Or
No, no,
is
for
it
all
containing multiple? Okay.
multiple, any will be saved in this file.
Okay, so once you did the curl, then for the API, your sorry, Gemini API file, all those information, this just it
Yeah,
keeps on
yeah,
adding on that cbom.json.
same file.
Okay. Okay, this is good actually. Yeah. And I
And
think
this,
why this can make one difference, Shubham, is nowadays, since see, this is not actually doing the network traffics thing, right? Not collecting the network traffic. It's actually doing on same uprobe level. With encrypted client hello, when we have client hello and its server hello both in encrypted format,
Mhm.
what do you think will come in the TCP dump? What do you think will come in the PCAP?
I think we can get
Right?
the same level of information with that with this tool as well
No, but
because
this
we are
tool
not.
is doing after the decryption. In some cases, it's once the data is decrypted, then it's collecting, tracing the thing, right? Such as your
Okay.
certificate. It's not so. Even though your client hello and server hello will come, this will trace once it's decrypted, right? Because in a way you have to show your application. This was the client hello. So everything that comes into your encrypted format at the end of the day, it has to be decrypted. So once it's decrypted, then it will trace it. I think that is the point. But when we
And
do like
same thing.
Zeek or TCP dump, it's doing while the network traffic is there between the network layer, not on a different layer. So network layer, I think client hello, server hello would still be encrypted, and we might not see. I'm not sure.
Any opinion on that, Satyam? What will
Yeah,
happen in the case of client
first
hello
of all, you
encrypted?
can see this log, right? c1.json 19 components. It is of 4 sessions. So all those
Okay.
4 sessions is in this.
Okay, great.
And again, I think so. You're talking about a different problem again because
Yes, maybe I
it's
have
not.
that in the agenda. I'll touch upon that point later. But yeah.
Yes, yes, that is entirely different. What you're talking about, TCP dump can do. Of course, you can do that. That is not the agenda. That eBPF cipher trace touches. You can get the same level of information there also. The difference is only the runtime component. So I would like not to confuse those parts. They can trace the same level of information, just the time is the matter. Like if you're tracing at runtime, then you need this. If you're just testing an application and you just want to just do a demo test, you can obviously use TCP dump for that. That is really optimal solution for those kinds of problems.
Got it.
Yes, I think we don't have much time. So if we for further questioning, Shubham, you and I can connect to Satyam after this call, right? Anytime.
Okay.
Yeah. But your question
Sounds
about
good.
encrypted client hello, I mean, it's point in the agenda. I will give like a brief explanation. Then maybe Satyam would be able to relate to that problem and then see where EBPF ciphertext stands from that point of view.
Mhm.
Cool. Yeah. Perfect. Yeah, so second thing is about the progress and presentation that is going on GPU-based PQC integration with TLS. So we have a new mentee now, Megha is on the call, and she has been doing her work on CU PQC, GPU, and how PQC workload can be used in the GPU thing. So yes, I think Mega, you have some slides. Maybe you can share them. I can do a very quick startup of kick off the presentation, and then maybe you can take over after this.
Hi everyone. Just
Hey,
a
Mega.
sec. Just a second. Wait.
Yeah, you might also have some system permission issue if you are sharing screen on this browser for the first time. Okay, didn't face any problem.
Is it visible?
Yes, it's visible, but not the presentation slide.
Oh, okay. Wait.
Maybe you can click on that window option and just directly share that window.
Is it visible now?
Yes,
Yes, yes. So
Okay, so hello everyone.
hello.
the
This presentation is about the progress that has been made in the CUSSL project.
Hmm.
And these are the things that I will be discussing in this presentation, like what is the project about and how much work has been done yet, the what benchmarks I have, benchmark results and other things. So as we know that uh, MLChem involves more computations than the classical algorithm. So the main idea of the project is to offload that computation into GPU while keeping the OpenSSL compatible with existing applications. And uh, the objective is not just to integrate GPU based MLCAM into OpenSSL, but also guaranteeing the thread safety and supporting asynchronous execution, and these like keeping full compatibility with the OpenSSL workflows and providing automatic CPU fallback when GPU environment is not set in the client system. So this is the architecture that I followed for the integration of CUPQC into OpenSSL. Suppose a client sends a request, TLS request, then the request goes to the modified. I have modified the MLChem source file. I just added a patch for the for integrating CUPQC into OpenSSL. So that request goes to that file, mlcam.c file, and then there it forwards the request to the CUSL runtime layer, which is the CUPQC runtime.c file. In the CUPQC runtime C file, it receives a request, then it doesn't directly send that request to GPU because GPU works best in batching. So it will wait for the queue to fill up, and when the limited amount of requests get filled in the queue, then the runtime will take that many requests as a bash to see CUDA backend layer, which is cupkc shim.cu file. This file is like a translation layer between the OpenSSL C file and cupkc c plus dot cpp file, because they work on different languages. And this batch is when it is sent to CUDA backend, it involves NVIDIA CUPQC library on the GPU, and then the GPU completes the execution, and the results are then returned to OpenSSL, and the handshake continues. So this was the architecture that I followed for the integration. And then here are some of the problems that I had to face and for which debugging was also done. So the first one is the blocking, like OpenSSL follows executes any cryptographic operations, like it receives a request and then it wait and then it returns the result. So sending, like it takes one call at a time, so sending one operation at a time actually wastes the GPU. So so we had to keep in mind that we don't just take one job at a time for 2 GPU. Instead we do batching for efficient throughput. And the second problem was from Nginx server, because I use Nginx for benchmarking. So Nginx creates multiple worker processes, and each process it has a separate memory. So batching the request from different workers, it's not natural. So we had to add code to do that as well.
I mean, I'll just add one more thing on this. So,
Yeah.
just in addition to it, so what she meant by batching is when there is simple TLS handshake. So let's say your TLS is still being done in the CPU, right? Your libSSL part is still the CPU part because it's the starting of TLS. And the point we are doing the GPU thing is on the algorithm level. So within the TLS, when we are using MLChem for encapsulation, decapsulation,
Yeah.
that is where GPU is used. So for just one TLS handshake, we have to send data from CPU to GPU. So just for one TLS handshake, we have to do this process transfer from here and there. So it will actually waste some of the resources, right? So instead of doing this, what she meant by batching is let's take some amount of inputs. Let's say it could be multiple handshake. There could be one batch size. And once that limit is touched, we reach to this limit of, okay, these are the number of handshakes or inputs. Then we send it to the GPU and GPU will then do the process. Otherwise, just for one TLS handshake, one operation, we using GPU. So it doesn't make a lot of sense, right? Yeah,
But
continue.
again,
Yes.
wouldn't that be a bottleneck for the operation, like for the connection maybe?
No.
Because you are holding some of the connection part, some of the decryption part, and waiting for some limit to cross. Then only you are decrypting or whatever operation you are doing in the batch format. So
Yes.
what will happen to that? The uh, you understand the point, right? I mean, like
Yes. Yes.
you're
Yes.
Yeah,
holding
good
some
question. Yes.
operations and for putting it in batches so that you can decrypt or do that operation later. But what will happen to that particular point of interaction?
Yeah. So that was the third like problem. So I will first explain it, then you can ask me if you got it not or is it relevant or not. So the so so as you said that might create bottleneck. So for that, OpenSSL has an async property, async job API, which is like I have done batching, then we take that batch to the GPU while the thread that was doing that was associated for that job will that thread no that job will be paused, the thread will do the CPU work, and when that job gets done in the GPU, when it comes back, then like wake up call will be there, and then it can resume from there, else the thread will be doing the other things.
And also, I think we have set like a time, a very minimum time of maybe like 3 microsecond, nanosecond. What was it, Mega?
300 microseconds for batch.
Ye- Yes. So one thing is if you cross that batch limit, it's fine. Let's say now there is no such there. Let's say there is only one handshake or two handshakes, right? So you can't wait for the whole batch to be completed. It might take hours. Yeah, it doesn't know. So we also have another counter that is like very minimum 300 microsecond, whatever it is. So let's say it's like a very small time. So within the 300 microsecond, if batches comes, it's fine. If there is no batches, then we'll continue the process. So the TLS handshake data from CPU to GPU will be go. We'll not just simply stop the process here at that point.
Got
Does
it.
that answer your question, Shubham?
Yeah. And this is something you are doing it from the OpenSSL APIs, right?
Yeah, OpenSSL API also, but also we can set the batching on the
Batch,
regardless of the yeah
yeah, batching is done
regardless
in
of
the
OpenSSL
runtime file.
runtime files. Yes.
And what about this time limit? You said this, or this is something that can preset?
Yeah, it can be reset. Actually, I set the limit.
Okay,
Yes.
I got it. You can continue, please.
Okay. And uh, like so I have told you about the architecture. So I was able to successfully integrate the CUPQC into OpenSSL directly by just adding the patch to OpenSSL source code, and then the CUPQC shim file and runtime file, and then I could see the handshake, and it used and with the benchmarking files I saw that it was using the GPU for encapsulation. So that was done with the integration. Then now was the benchmarking part. So for benchmarking, I first thought that because I couldn't get the very large number of very large operations per second. So I thought it could be because of the PCIe transfer. But when I actually measured like the numbers, where was the bottleneck? So it was not the PCIe transfer. It's PCIe transfer just used 6% of the time that was being used. And the main issue was with the kernel launch itself, because I uh, launched GPU kernel for a single MLCAM encapsulation. uh, that is the worst case for a GPU, because GPU is multi-threading. So kernel launch used around 94% of the total time, and it showed that it was using a lot of time, and that was the bottleneck. So this was the issue, not the PCIe transfer. And then
And I
how the
also think, just sorry
yeah,
to interrupt, I also think that, yeah, if your system, if your company doesn't have a lot of TLS traffic, of course, they will never touch the GPU. I mean, just for small handshake, small number of handshake, for, for regular times, it doesn't make sense. And this is basically the one who will be using this is
yeah,
maybe like the big heavy load web servers, which do thousands of TLS and six, millions of TLS and six in some seconds. So that is the target audience. So
Can you back up page before?
what,
go
Can
back
you
to the
go back?
previous slide.
yeah.
Yeah. So first tell me like what is the architecture? What is the network setup you have? And based on that, I have some questions. Like which component is running at where? Do you have a multi-VM setup or you are doing everything on a single system?
On a single system.
Okay, and what do you mean by like kernel launches uses 94% of what?
The total time for encapsulation, like taking the job from CPU to GPU and that bringing it back.
You could GPU then bringing it back. And how you encounter this?
Will have to work on this.
Okay, okay.
Yeah.
Yeah, I mean, maybe I think what I'm understanding from what you're saying, Shubham, is you're saying that what do we exactly mean by kernel launch, right? Because so it's basically saying it's if it's not the PCI transfer, okay, it's
Yeah.
the whole time is 6% of the total is of the I think whole TLS handshake, right? 6% of the total time. So
N-
in that case, yeah, am I right or wrong?
Not just TLS, just encapsulation.
Or just encapsulation.
Yes.
So by kernel launch, I maybe you mean like the step in the kernel which is starting the sending of this data from CPU to GPU, right?
Yes, and then there, if it has very less amount of jobs, so then GPU will be idle for more time.
Okay, so yeah, but why does it take this much time? I mean, why the kernel launch itself is taking a lot of time?
Maybe because of the less number of job requests. I, I will have to look
Y-
into.
Yeah, I mean, regardless of how many jobs you have, if you want kernel to launch something, the kernel will launch, right? Or is there like a standard thing between CPU to GPU that if the data is not this heavy, it will wait for some time and then, I mean, if it's like a standard thing between CPU to GPU connection, then maybe we can understand. Yeah, but yeah, you'll have to check a bit more on this.
Yeah.
Yeah, but I'm happy to see like the PCI transfer is not taking too much of the time though.
Yes. Okay, now then this slides explain like how batching is done. So I have already explained that when jobs comes to the GPU, then the GPU will wait, no, not GPU, to runtime file. Then the runtime file will wait for a certain amount of time, which I have used here 300 microsecond. Or if, or it can wait for, like, if I have a limit of 16 requests, then it will wait for 16 requests. So it depends if the time is up or the requests are filled, then it will take the batch is then sent to GPU, and then their encapsulation happens, and then it comes back, the result comes back. Now from here onwards, all the slides are the benchmark results. So this first slide is the comparison between CPU and GPU raw encapsulation results. So this is for like if we are just ignoring all the latencies of TLS handshake, we are just focusing on the raw encapsulation, how much GPU can do or CPU can do. This is the benchmark, and we can see that with if batching is not done, GPU performs worse than CPU, and when batching is done, like for 512 threads, we got 120,000 encapsulations per second, operations per second.
Yeah, this is like the maximum capacity of GPU, right? 512 threads
Yeah,
running at the same time.
yeah,
And this is for a fixed number of operations and time limit, right?
yes,
It's per second, right? Per second.
yeah, yeah, per second.
Okay.
Yes.
And is this slide shows the graph shows that when the batch sizes increase, so when the threads are increased, concurrent threads are increased, so how the GPU batch size, average GPU batch size increases or decreases with that. So this is the graph, like for 512, the average GPU size, average jobs that are in one batch is 103, and for less threads there are less jobs per batch. And the right side, the graph shows the results for CPU and GPU operations per second. So we can see that for less threads, the CPU is creating more encapsulations per second than GPU, but for more threads, the GPU is obviously winning. And CPU, the operations per second for CPU decreases as there can be context switching overhead or cache thrashing overhead.
But on this, like, I don't understand. Like, the second graph, this is CPU operations per second, and on the bottom side is the OS threads. But we don't have these many of threads when we take the CPU thing, right?
Yeah,
CPU
that's
is mostly F4, but why does the graph shows, I mean, for all the OS threads?
I think it is taking like not threads but jobs, maybe requests.
Okay,
I have
five.
one doubt.
Okay,
Uh,
yeah.
why is it that as CPU threads are increasing, why is it the number going down?
Because of the limitation of CPU threads. So in the system that I am using, it has four threads, maximum four threads capability. So it is because of context switching and overhead and cache thrashing overhead, I think so.
Also, this is a problem with OpenSSL. So with OpenSSL, with if you use multi-core, then performance decreases. So this could be something OpenSSL specific.
Again, like if we have more threads, more
Yes,
threads, again, like it should be. I understand, like the performance decreases, but it should the number should be better than the previous one.
Like you're saying
that
that
is
if I have four cores
Yeah.
processing some X amount of requests, then eight cores would be processing less than X. Like it really does not make sense because if we have most better CPU, that means you'll be performing bad in processing the handshakes. Whereas GPU goes like it peaks after 128.
Yeah.
And one more
but
question,
yeah,
Satyam, just from the hardware perspective. So,
Yes.
same number of core, same number of threads in CPU and GPU. The
Mm.
performance of GPU will be less than CPU. Is that Will
Yeah,
true or
for less threads, GPU performance is less than CPU here.
So
Yes, yes, Subham.
16 threads can handle 73,000 requests.
Yes.
Okay, and 512 threads would only handle 56,000. So why not just in 512 threads, why not just use 16 threads and get the same performance? Like this is what how OpenSSL works? Is it like something
No, no,
issue with
no, no. This there might be some problem with this graph, but also like how did you even like come to this, right? CPU only has 4 threads, so is this like a hypothetical calculation, or is it like a CPU thread, or I don't know. You meant job, but what is job? I'm not sure. And yes, OpenSL, the performance degrades, but it doesn't come down to the previous calculation. Of course, let's say if it was improving by the percentage of 1.5, it
Mm.
will increase by the performance of in multi-core, let's say by 1.2 percentage. So the performance degrades, but it doesn't go down.
Okay, I'll look into it.
Yeah, I mean, I'm not very confident with the second graph. So in the left side, you have these are the encapsulation operations, right? The number of operations on the left side. On the
Yeah,
this is called y-axis or x-axis? This is y-axis, right?
it yeah, y-axis is the average batch size.
Okay, okay, yeah, yeah. Average batch
yeah,
size.
and I think like left side graph is also something not adding up. So with increase in the number of threads,
Yeah.
uh, with almost same level of batching size, CPU batch size, the
Mm.
performance should be a little better.
Uh,
Or
um,
I'm not sure. Like, can you explain a little bit more about it?
Yeah, can you explain the left graph if possible?
yeah. So I told you about like we are creating batches and then we are sending it to GPU. So this I told you about. We have set a limit of 300 microseconds. So with 16 threads, if the time is up or the 16 requests are there in a batch, then the batch will go to GPU. So this is the average batch size. So like in one batch, how many threads are there? How many requests are there?
Okay, so this 16 number is your batch size,
Yes.
right? Okay,
Yeah. 16,
six.
36, 31, and 103.
Okay, this
And
is your batch size.
with
Yeah.
increase in overhead, the batch size will decrease.
No, increase with 128. I think some of the operations could have lost or something like that.
Means there may be some noise with that.
Yeah. Yeah.
Yeah, I mean, this is possible.
Yeah. Else
Mm.
it will be increasing.
Yeah, but
But
left,
again,
right. But this OS thread is, I think, this is the number of uh, TLS handshakes that are coming for the GPU, or this is, I don't understand the left graph.
because
This is
see, like, the number of threads are increasing by two, from 64 to 128. Even though there may be a lot of noise, the batching should be a little higher. I think from the logical perspective. But again,
yeah, it was higher as well. These are the just results for I have done so many benchmarking. So 31 was one of them, and then it was increasing for other.
Yeah, I think she has like a good report of that in the doc format, so maybe she can share all those documents to us as well after this
okay.
meeting. And maybe in the next meeting, Mega, you can come up with the like updated version, or the
Okay.
version, the same graph, but with more confidence and more results. Maybe that,
Yeah.
and with more explanation, maybe.
Okay.
I had one more thing to ask. Like, do you think like if the traffic is really low, then handing over the encapsulation and decapsulation to GPU is actually worsening the performance? Like, is there like set size, something like that? That if we have traffic lower than this critical point, then offloading the encapsulation and decapsulation to GPU actually worsens the performance. Is it
Yeah,
something like that?
I haven't set that limit, but we can set that limit.
Okay, means that something like this exists, right?
Yeah.
Yes. I think, see, for GPU, we have to uh, I don't know, we have to wake up the GPU for these tasks, right? And if it's just like a single operation, GPU was never meant for the single operation, right? It just
Mm.
throws everything with all the threads. So of course, if it's just like a small number of handshake, then it will worsen the TLS time. It will worsen the TLS time, of course.
Then I think so. Then maybe we can make a scheduler kind of something like that out of these metrics. That if the throughput is more than this, then offload it to GPU, else keep it to CPU. Something like that we can do.
Yeah.
Yep. Yep. Yes. We have the fallback, but we don't have the, what is the term? This
Limit.
switching.
Yeah.
Yeah, limit switching. Yes. Fallback is when GPU is not ready, then okay, CPU handle all the things. But this is just fallback. We need more advanced than this. What Satyam is saying. Yes, it makes sense.
Yes. These results are from the official OpenSSL benchmarking tool, like OpenSSL speed command. So when I ran that command, I got this output. So we can see that for less bad threads processes, the CPU definitely wins over GPU.
So this is whole TLS, is it?
This is yes.
And then those CPU are like the four CPUs. I mean, four threads.
Yes. Not yes.
Uh, can you explain the graph a little bit more? Like, I don't understand the what the performance is, and also a little bit about the tool itself, what it actually does.
So OpenSSL speed is the benchmarking tool which calculates like encapsulation, key generation, and decapsulation.
Okay.
It gives per
Mm.
second operations.
Yeah, so it's an official OpenSSL tool,
Yeah.
OpenSSL speed. This does the benchmarking.
Yes.
What is no MPS?
MPS is multiprocessing server. Like it is used to increase the scale, like more throughput. It is used to increase the throughput. So even when I used MPS, still I couldn't get better GPU results.
And the y-axis denote the batches. Is that correct?
No, y-axis denotes the operations per second.
Oh, okay. So focus. What is fog processor here? Increasing like
Uh, it,
what is fog process here? You're creating something. Yeah, I mean like a little bit of fog process. I forgot about it.
Forked process, is it?
Yeah.
Mm. Is this
And something
and
up
this is
in the Java
multi
class. What
and
was
forked processes? Not sure. Do you have any idea, Mega? What are these forked
no.
processes? Okay.
yeah, I think you should. Okay, so before presenting, I think you should look into the terms and things that is actually you are presenting because there will be some questions which you
Okay.
maybe ask because the user, the people who are actually looking into your presentation will not be aware of those terms, completely new of it. So yeah, I mean,
Yeah.
Yeah, and also it would be better if you could just mention like x-axis means this, y-axis means
Yeah.
these operations.
Right.
I think it would be better in that case.
Yeah, I'll work
And
on that.
then, yeah, and then this is 1632 threads. So when there are 32 threads, there will be, okay,
But
okay,
This this is thread or fork process. What is exactly the x-axis?
It I actually just used the speed benchmark tool today only for the results, so I will look into it.
Okay, okay. No.
yeah, but still,
Also,
comparatively, 32 thread in GPU is very less. You won't get the best quality result with this.
yes,
Yes.
also
You have
one
to,
more thing. I think so. The high point of like the benefits of a GPU is having a lot more threads compared to a CPU, right?
Yes.
That
Yes,
is the whole point, right? So we match them with the same amount of threads. I think so. Of course, CPU would win.
Yes.
yes. Yeah, but we also saw that previous graph, right? In which, can you go back to the previous slide in which you were, yes, this one, right? The GPU threads, we were using all of that. So you see the result. And again, you see the third box and the fourth box. If it's like a same amount of CPU and GPU threads, operation is very less.
Yes.
Yes.
by the way, Satyam, from the system architecture perspective, why GPU should have lesser performance than CPU
Yeah, because
having same thread?
GPU's threads are like brainless bots. All they can do is calculate very fast, and because there are a lot of them, their calculations are really fast. But CPU's threads, they have to do a lot of stuff like managing your VRAM, then managing your memory, everything. GPU cannot do what the CPU can do. CPU is doing a lot of different types of tasks, and that's why its threads are really hard, to have a high number of them. But GPU, all it does is calculate, multiply, do this, that. That's it. That's why having a lot of threads, it can do calculations very fast. That's the only up point of a GPU. That's why it has a very specific use case, like for having a good display, playing games, and then LLM, because there is matrix multiplication in it. Besides from that, a CPU's core and threads are more capable of doing different kinds of tasks. GPU is not meant for those kind of things.
Got it. Yeah,
And
very
do
clear.
we also have a higher end system where we can run this CU Shankar and Shubham, maybe for a few days? The one from Supermicro.
Yeah, correct. Good solution
Yeah,
there.
does it have GPU?
Shankar could better answer that. Shankar. Yeah, anyways,
Yeah,
I
it
think
does have. I guess, yeah.
Yeah. For how
It's all
long
about
we have the
GPU
system
because
access?
mm, maybe till 12 or maybe till today, I'm not sure. It was 10 or 12, I'm not sure about the exact date. But we can book it
Yeah,
again. I mean, all of us have the IDs, so we can just book multiple servers and use it if you want.
yeah.
I tried
And I
the
think,
I tried to run the NVIDIA CUDA end, but I faced a lot of issues. So it was
mm,
be like almost the whole
okay.
week.
Yeah, check the system last date. If it's 12, then give the access to Mega. I think what Supermicro also provides like some very high-end servers which have Bergamo chip, like 256 cores, 128 cores. So we can also do testing in there. And yeah, comparatively, GPU threads would definitely be higher, but yeah, but we have still not just four cores, we have twice, four times, six times of it, 256 cores. So maybe we can do testing there as well.
yeah,
Yeah, I'll also have a look because we have ID, so we can book anytime. Yeah, earlier because yeah, earlier we were in the process of development, right? So it was
Mhm.
not possible to develop and then test. Right now the development is done. We have to do benchmarking testing. So right now it's a good time to schedule CPU because we don't have to develop, we just have to run there.
True. Okay, we'll
Yes,
have to schedule some VM some servers for the same.
sure. So Mega, is that it or any other slides or many?
This is the, like, till now we were benchmarking encapsulation. This is the full handshake throughput benchmarking. So while the raw encapsulation gave us like maximum 1,20,000 around encapsulations, but when this was like we were checking it for TLS full handshake, then we it came down to like 1,000 1,500 encapsulations because of the other latencies, other overheads like TCP, then runtime overhead and batching things. So it,
And did you utilize all the 512 threads of GPU or no?
yes.
But I think there wouldn't be that amount of client request from the client side that could fulfill that could use all the GPU threads,
Mm,
right? I mean, there is also a limit to the client handshake that we can uh, create from the client side, right?
I created around 9,000 handshakes,
Mm,
and there were 64
9,000.
client threads. So we got this encapsulation number.
Yeah, still, I think still the number should be higher to
Yeah,
get the better performance of GPU.
yes, we can shift to different another servers for async servers, or we can have a better hardware system for that.
Mm.
Then these are all the benchmark numbers, and these are like the problems that were faced. So I did debugging for that, for these problems, and then we could get these numbers. Yeah, that's it. And so further we can do, like, we can get async native servers for to get higher numbers, and we can definitely get newer hardwares like Gen 4.5 to reduce the latency for PCIe, and we can also publish a research paper for this once we are done with this.
Yes, yes. I mean, whatever the result come, this whole process should be come under as a research paper because this is most of research work. So our final goal with this task is to end it with a research paper that we can publish later. So yeah, that is still the goal.
Yeah.
Yeah. But before that, I think we'll have to do this testing on big end servers, like the one we will get from Supermicro. Yeah. Otherwise, we are not able to get it too much. Yeah. If the kernel launch that you say
Yes.
is taking too much of time, if we can try to reduce it, then even in the this current environment, we can get more
Kernel launch,
TLS and 6 per second.
yeah, kernel launch can be reduced with like providing GPU with enough numbers, enough jobs.
Yes, and we don't have enough jobs at the moment. Or are you saying that we also assign some other non-crypto related jobs to the GPU at the same time, so the
We can
process
do,
keeps on continuing?
yeah, we can do, and we can use different, like we can upgrade the servers first, and we can also do with that.
Yeah, but whatever the result is, this is interesting research actually. So yeah, nice presentation. Maybe we can have another presentation in next quantum security meeting where you can update these slides, make the graphs more easier to understand, and the numbers, benchmark numbers should be more, you should be more confident about that. So we
Okay.
can we can do that in the next meeting then.
Yes.
All right. I think I had few other things, but the time is already up. I don't want to take too much of your time today. Also, it's Friday evening, so I know Shankar has to pack up and go for a trekking. So yeah, I won't I won't be taking too much of time. Yeah, other things were like similar, small things. Some PQC-A updates that Shubham and I are doing, and future mentorship work. I wanted to discuss on encrypted client hello, and this wonderful blog that I saw from Netflix, uh, because it was doing the dependency. And right now in crypto inventory world, dependency is a very big issue, and not everyone is able to solve it. Like dependency, deduplication, everything is there. So I was trying to take some inspiration from that blog. But these are all interesting topics. There was one CISO guide to post-quantum cryptography that I really wanted to discuss in this meeting, and then some more posts from Cloudflare. So we'll leave that for the next quantum security meeting, right? It's bi-weekly, so next to next week we'll have a meeting. And I would request all of you to join because it's going to be very interesting. Yeah, I think we got good audience today. 10, I think more than 10 people. But by the time the meeting took more of the time, we some of them left. But it was a good presentation, good audience, good points discussed. Thank you.
Yeah, great presentation, Mega. And, yeah,
Okay, guys. Yeah. Shall I stop the recording or shall I leave and it will be stopped automatically?
so maybe let me just stop it.
I've stopped it.